This video is basically a video of a PowerPoint presentation which can be found if it's Physics 110 under Supplemental Materials, Fox made. So this is a video on how to add vectors, and there's three basic ways that we're going to go about doing it. One of them is the graphic method, and that's what I refer to as drawings right here. And then there's the algebraic method and trigonometric method. I'm going to touch on the trigonometry. I'm not going to go into that in great detail. There's another video out there if you really desperately want to know. If it's Physics 110, it's definitely not required. If it's Physics 131, 151, or 251, then definitely you need to know how to do the trig piece of it. However, for Physics 110, not. In algebra, you're adding like components. If you start with the polar form, getting to the rectangular form, that's not necessarily something that Physics 110 students are expected to do. However, 131, 151, 251 are expected to be able to do that. However, once it is in rectangular form, yes, Physics 110 students, I do expect you to be able to add them. But primarily, we're doing the drawings here, and then we'll do some basic algebra and trigonometry. All right, so when adding them, recognize that we're going to represent these vectors as arrows, that there's a magnitude represented by the length of the vector and then pointing in a particular direction. So we need to somehow come up with a scale to represent what's physically going on, a physical reality or a problem reality with a representation on the screen. And so something that has, if we're dealing with displacements, a vector that is a magnitude of 2 meters will be twice as long as a vector that represents 1 meter. And so doing graphically, the length should be proportional to the actual magnitude. The direction needs to point in a specific direction. Direction does matter, so it does matter if I have 2 newtons going this way versus 2 newtons going that way. That will have very different effects on an object. And then working on the idea that vectors that are the same magnitude, the same direction, in other words, they're drawn the same length and have the exact same direction as another vector, we're considering them equal. Now, if you want to consider them the same vector or not, that's up to you. For instance, the number 2 and the number 2, are they just two numbers that are equal to each other, or are they identical numbers? I'll let you philosophically decide that. Now, if I take a vector and I move it around, as long as it has the same magnitude and direction, it is considered to be the same vector, and you move them around putting head to tail. So we'll be doing the head to tail method or tail to head method, whichever way you want to word that, traditionally worded head to tail. So let's start out with just the simple one-dimensional problem with just two vectors. I got a car traveling 100 kilometers east and 40 kilometers west, and from my point of view, I'm going to consider east that way and west that way. However, it's possible that the video that you're seeing is flipped, but you'll see which way I consider east in the next slide. So we have the two vectors, 100 kilometers and 40 kilometers. We'll represent that by some scale, and whatever scale we pick, the one going west needs to be 40% of the one going east in terms of length. And there we are. So that establishes my east and west right there. If I move them around as I do down here, notice that those two vectors have the same magnitude, same direction. I'm considering them the same vector. When I add them, I can start with either one when I'm adding them. So first off, I'm just going to start with the one east. So I pick a starting point, I draw the vector, and then I take the second vector and do the head to tail connection right where I'm circling. And so I put the tail of the second vector at the head of the first vector, and I end up here. So you can imagine that if you walked 100 kilometers in one direction and then 40 kilometers the other direction, you end up here. The resultant is where are you relative to where you started. So we started here, and we ended up there, as is represented by the solid green arrow with the bold-faced R. Using bold-faced here to represent vectors because the equation editor in the Microsoft products is frustrating, and so I'm just sticking with bold for this. So I ultimately end up with 60 kilometers east because I end up 60 kilometers east from where I started. If I had done it the other way, started with the west vector, so the red vector first, and I added that one, I'd end up here, and then I put the tail of the blue vector at the head of the red vector, and I end up in the same place as I did before. Ultimately, my resultant is from where I started to where I ended, and I still 60 kilometers east. It doesn't matter which one that you do first. This is known as commutative property of addition, so the way that you would more formally word it as that the commutative property of addition holds for vectors. vector addition and scalar addition, as in 2 plus 3 is the same as 3 plus 2. It's commutative property. Just sometimes the vector addition has slightly different rules than scalar addition, especially when we get to multiple dimensions. All right, so now let's take three vectors. So still a one-dimensional problem, so everything is going to be moving basically in this problem east-west. We could, pick any particular line, so just so long as all vectors are going in the same direction or opposite each other, there's nothing at some strange angle relative to another one. And so I have two pointing east, I have one pointing west, and so when adding them graphically, it is good to represent this. So whatever scale that we are using, the 100-kilometer one should be the longest one. That should be 60% of the first vector, and that should be 40% of the first vector, or 2/3 of the length of the third vector. And as such, I have drawn them. So I'm using the scale. 1 centimeter is equal to 10 kilometers, which I think is the same way I used last time. And so this would represent the 100 kilometers east, and so on. Again, I can rearrange them, so the order does not matter. We still get the same answer. And so now I add them. I start with a vector. It doesn't matter which one with which I start. I don't have to start with 100 kilometers, but I happen to in this case. And I drew the first one down. And so now head to tail, where the first vector ends, I start the second vector. And then where the second vector ends, I put the third vector, and I end up here. So ultimately I end up here relative to where I started. I end up to the right, as is indicated by the red resultant vector right here, the bold red resultant vector right there. And then given our scale, that red vector is 12 centimeters long, which would represent 120 kilometers. Now, if you actually measure it on the screen, it's not 12 centimeters, it was 12 centimeters in the drawing that I had done. Now let's go to two dimensions. So I now have one that's going northeast, one that's going west, and one that's going south. And so adding them graphically, it's the exact same process. First you set up a scale, then you draw the vectors down in the correct direction, at the correct magnitude given your scale, and then you add head to tail. And there we go. I first draw them down, giving the exact same scale as I did before. This is the northeast, assuming, again, east is to the right and north is up. You could also have done I hat, J hat. It works just as well, but east, north, why not? So I have my three vectors, and then we add them. This time I started with the south vector. And then I added the west vector, so notice where they meet, the head to tail, so the tail of the second, next to the head of the first vector I drew there. And then, again, head to tail, and I end up here relative to where I started. So that would be my resultant, as is indicated right there. Now the length of it, I could tilt down a ruler and measure the length of that, and then using my scale figure out what the actual size is. And so it was 3.25 centimeters, which represents 32.5 kilometers. And then to get the angle, if this were physics 131, 151, 251, yes, I would expect you to be able to figure out what that angle is with something more sophisticated than just straight up measuring. However, in physics 110, it'd be great if you can do that. However, just putting down a protractor on there and measuring the angle works well enough, and it's a 19.1 degree angle. So my resultant, 32.5 kilometers, 19.1 degrees. I give a magnitude and a direction. That is the answer in polar form, where I give a magnitude, direction is known as polar form. Now we got the one-dimensional two vectors doing it algebraically. So this is a small foray into algebra. So we establish a positive direction, which I'm just going to make east as the positive direction in this one. And because it's a one-dimensional problem, I get away with indicating direction with just a plus or minus sign. I don't have to use I hat or J hat. Like my 100 kilometers east becomes positive 100 kilometers. My 40 kilometers west becomes negative, and if you don't see the negative sign, it unfortunately got caught over here. So that's negative 40 kilometers, and because the negative indicates that it's to the west. Now, you would just add it straight up. So positive 100 kilometers plus negative 40 kilometers, and mathematically this is the same. 100 plus negative 40 is the same as 100 minus 40. In other words, 60. My answer is positive, and I said positive was to the east. So the resultant, 60 kilometers east. Now, having already established that east is positive, if I actually write that out, then I could get away with just positive 60 kilometers. I don't actually have to write the word east again. One-dimensional, two vectors. If I had chosen west to be positive, giving the traditional brainwashed map versions, since west is always to the left, then I make that positive. Then it's now a negative 100 kilometers, positive 40 kilometers. If I add it up, I get negative 60 kilometers. Now, since west was positive, negative 60 kilometers means it's east 60 kilometers. And so I get the exact same answer. Now, again, having established west as positive, if I actually write that out, then I can get away with just negative 60 kilometers as the final answer. I don't have to then put the actual direction in there if I define what positive and negative is explicitly. Go to the two-dimensional problem. Now, in class or in other videos, I use I hat and J hat, and those are really convenient because the hat automatically indicates that we are talking about a unit vector. But again, the equation editor I find very frustrating working with Microsoft products, and so I'm going for boldface, but my boldfaced I and my boldfaced J are representing unit vectors I hat and J hat, and I went ahead and just defined I hat to the right, J hat up, letting this be north and east. So now north can now be represented by J hat or bold J. West is negative I hat, because I said east was positive, and then south, negative J hat. Now notice this negative 40 kilometers I hat, because on the other page I might have made it sound like 40 kilometers negative I hat. Recognize that even though writing it like this is mathematically okay, it makes it a little bit more difficult when it comes time to doing the addition. And so it is traditionally written, the minus sign is put up front, and negative 40 kilometers I hat is the more traditional way of writing it, and it also makes the math a little bit easier when it comes time to adding like terms. Trouble with writing it this way is that some students have the habit of leaving parentheses off, and so they would write 40 kilometers minus I hat. That's a subtraction problem. That is, one, you have a scalar minus a vector, which you can't do, or math people haven't told me how to do it. And also, this is not really what you mean. So that is just bad notation. This is awkward notation. This is the preferred and easier notation. So now our adding, we're going to add these three vectors together. So I have the positive 100 kilometers J hat, negative 40 kilometers I hat, negative 60 kilometers J hat. Now we just add like terms. I got J hat and J hat. I add them together. I get 40 kilometers J hat because that's 100 minus 60. And then the I hat I can't add in here, so this just leaves it as negative 40 I hat. This answer right here is done. We don't have to do anything else to it because I didn't specify what form I want the final answer in. This is rectangular form and is perfectly fine just so long as I hat and J hat are defined. If we want polar form, or if I had asked for what is the magnitude of it, well, you can do a little Pythagorean theorem, because this would represent 40 kilometers up or north, and then 40 kilometers west, and then we can get the total magnitude with Pythagorean theorem. R squared is equal to 40 squared plus 40 squared, and that is 56.6 kilometers. And to find that direction, again, 131, 151, 251, they're expected to be able to find that angle. In this particular case, you should be able to do it because of it's an isosceles right triangle. That would be 45 degrees. And so the direction of this, given that 0 degrees is this way, and that's 90 degrees, that's 45, you would write this as 56.6 kilometers, 135 degrees. Because when you're doing angles in polar form, it's always from the positive x-axis, and so that's the angle that's being represented right there. There are other ways of doing it, but that's the standard convention. Again, what the final answer is telling us is not the movement, but where the object ends up relative to where it started. It's the displacement of the car. In this particular case, it is not saying that the car actually traveled 40 kilometers north and then 40 kilometers west. It's just it ends up 40 kilometers north and 40 kilometers west of from where it started. Now the trig, we're not going to do a lot with the trig. So if you're curious, there's another video with addition of vectors where I actually get into some of the trig of it, and so I recommend that you look at that. It should be in the list because the first part of it definitely is within scope of the first 5 minutes or so. It's definitely within scope for physics 110, and the rest of it is out of scope. One of the big methods with trigonometry is when you're given the magnitude and direction in polar form, so just magnitude and an angle, that you put that into I hat, j hat components, and then you add them in rectangular form, which we did earlier. And another method of doing it with trigonometry is avoiding that step and just using law of sines or law of cosines. And I believe that is it. So